三、二、一，点火！起飞！
China has made history, successfully landing on the unexplored far side of the moon.
Chinese scientists have proposed something wild. A radio telescope made of thousands of antennas on the moon's far side. About 7,200 simple wire antennas would be spread across the surface like a metallic spiderweb. The goal is to listen for signals from the universe's dark ages, before the first stars ignited. Here's how it would work and why it matters. What are the cosmic dark ages? The cosmic dark ages are one of the most mysterious and least understood chapters in the history of our universe. A vast, silent era that stretched on for hundreds of millions of years after the Big Bang. Imagine the universe not as the glittering landscape of stars and galaxies we see today, but as an endless, lightless ocean of cooling hydrogen gas. No stars, no galaxies, no planets, no light except the fading afterglow of the Big Bang, stretched into microwaves by the expansion of space. This period wasn't just dark in the visual sense, it was dark in the scientific sense too, because we've never directly mapped or observed it. All we have are subtle clues, faint radio signatures, and theoretical models that give us a glimpse of what the cosmos was like before the first stars ever flickered into existence. Right after the Big Bang, the universe was unimaginably hot and dense, a swirling plasma of particles and radiation. But as it expanded, it cooled rapidly. By about 380,000 years after the Big Bang, temperatures finally dropped low enough for protons and electrons to combine into neutral hydrogen atoms, a moment known as recombination. This changed everything. Before this point, photons were constantly being scattered by free electrons. Afterwards, the universe became transparent for the first time, releasing the cosmic microwave background, the ancient light we can still detect today. But even though the universe was now clear, it wasn't bright. It was, in fact, pitch black. That's the beginning of the cosmic dark ages. During this time, space was vast, empty, and extremely uniform. There were no bright objects, no bursts of fusion, and no heavy elements. The only matter that existed was hydrogen, helium, and a tiny amount of lithium, the simplest elements created in the Big Bang. They filled the universe like a thin fog, cooling slowly but steadily as the cosmos expanded. Gravity began pulling tiny density fluctuations together, slight ripples left over from the earliest moments of the universe. But these clumps were still far too small and too cool to ignite into stars. It was a universe waiting in slow motion for something to happen. The only signals coming from this era were incredibly faint radio emissions from neutral hydrogen, particularly at the 21-centimeter wavelength. These emissions carry incredible information about the structure and temperature of the early universe, but they're astonishingly difficult to detect because Earth's atmosphere, our own radio noise, and even the Milky Way's background hiss overwhelm them. That's why humanity has never produced a direct map of the Dark Ages. We can see before it, the cosmic microwave background, and we can see after it, the appearance of the first stars and galaxies. But the Dark Ages themselves sit in a kind of observational black hole. Still, we understand this era conceptually as the quiet, formative period when gravity began slowly assembling the scaffolding of the large-scale structure of the cosmos. Tiny overdensities in the hydrogen fog started to collapse inward, forming the seeds of what would eventually become galaxies and clusters. Dark matter, which makes up the majority of matter in the universe, played an essential role here. It created the invisible gravitational wells that hydrogen gas pooled into. Without dark matter, the first stars might never have formed at all. But despite the slow and silent tone of the Dark Ages, the stage was being set for one of the most dramatic transitions in cosmic history, the cosmic dawn, when the first stars lit up the universe. These first stars were nothing like today's sun. They were massive, short-lived giants, hundreds of times larger and millions of times brighter. They burned intensely hot, producing ultraviolet radiation that tore apart the hydrogen fog around them. These early stars were so powerful that they started changing the chemistry of the universe, forging the first heavy elements in their cores and blasting them outward when they exploded as supernovae. But all of that comes later. During the Dark Ages, the universe was quiet, patient, and slowly evolving, like a cosmic embryo developing in darkness. The hydrogen gas grew colder. The density fluctuations deepened, and space itself kept stretching outward, making the entire universe larger and more diffuse. Time felt almost frozen on human scales, yet every passing million years brought the cosmos a step closer to the moment when light and structure would finally burst into existence. This era lasted for roughly 100 to 200 million years, possibly longer, depending on when the first stars actually formed. And because we still can't directly observe it, the Dark Ages remain one of the great frontiers of cosmology. Scientists are developing new instruments, some placed on Earth's far side of the moon to escape radio interference, just to listen for those faint hydrogen whispers from the deepest past. If we can map them, we'll finally fill in one of the biggest missing chapters in our cosmic story. For now, the cosmic Dark Ages remain a vast, hidden realm, the silent night before the first dawn in the universe. Why the far side of the moon? When scientists talk about mapping the cosmic Dark Ages, they always point to one location as the ultimate dream spot, the far side of the moon. And at first that might sound dramatic, almost like science fiction, but the reality is simple and astonishing. If humanity wants to hear the faint whispers of the early universe, we need to go somewhere quieter than anywhere on Earth. And no place in the entire inner solar system is quieter, more radio silent, or more protected from human interference than the lunar far side. To understand why, you have to imagine what the universe looked and sounded like during the Dark Ages, and why detecting that signal is so unbelievably difficult. The entire universe during the Dark Ages was filled with neutral hydrogen, releasing a faint type of radio emission, the 21-centimeter line. This signal is the key to unlocking the missing chapters of cosmic history, because it carries information about temperature, density, and structure before the first stars existed. But this signal is old. So old that the expansion of the universe has stretched it from roughly 1.4 gigahertz down into frequencies below 100 megahertz, often dipping into the tens of megahertz. Those extremely long wavelengths are the problem. On Earth, almost every artificial signal contaminates them. Radio broadcasts, FM stations, television towers, Wi-Fi, satellites, radar, military communication, even handheld electronics. They all fill the sky with electromagnetic noise. Our civilization is unbelievably loud to a cosmologist. If you tried to detect the Dark Ages signal on Earth, you'd be drowning in interference billions of times stronger than the signal you're looking for. Even the most remote deserts and deep valleys can't escape this pollution, because radio waves travel far, bend around terrain, and bounce off the ionosphere. Earth's ionosphere itself poses a second problem. It absorbs and distorts low-frequency radio waves. Below about 30 megahertz, Earth's atmosphere becomes essentially opaque. The Dark Ages signal lives right in that range. It's not just a challenge, it's physically impossible to see the full signal from Earth's surface. This is where the moon becomes absolutely critical. The moon has no atmosphere, so it doesn't block or distort the ultra-low frequency radio waves researchers need. But more importantly, the far side of the moon acts like a giant natural shield, because it always faces away from Earth, locked by tidal forces, so its rotation matches its orbital period. It never sees the direct radio emissions from our planet. When a telescope sits on the far side, the entire bulk of the moon blocks radio noise from Earth like a massive, perfectly placed barrier. No radio stations, no satellites, no interference from the International Space Station, no GPS, no cell networks, no military radar, just pure, undisturbed cosmic silence. Scientists often describe the lunar far side as the most radio-quiet location in the inner solar system, and that's not an exaggeration. Spacecraft from NASA, ESA, and China's CNSA have all confirmed that radio noise drops dramatically once a probe moves behind the moon. Modern measurements show that the far side is so shielded that even ultra-sensitive receivers detect almost nothing from human activity when the moon blocks Earth. That kind of silence simply doesn't exist anywhere else, not even in deep space. Free-floating instruments in space still have to deal with the constant bombardment of radio signals from Earth's satellites, orbiters, and communications networks. But the moon's far side is protected by solid rock stretching more than 1,700 kilometers across. Nothing gets through that. But the far side offers even more advantages. With no atmosphere, a lunar radio telescope can detect frequencies that Earth blocks entirely. And because the moon's environment is stable, quiet, and shielded, instruments could operate continuously without the constant interference that plagues Earth-based observatories. Even human settlements wouldn't disturb it. Any future moon bases would almost certainly be on the near side or poles where sunlight is accessible and Earth communication is easy. The far side would remain pristine and quiet, a sanctuary for cosmology. Of course, building a telescope there isn't easy. The far side has no direct line of sight to Earth, meaning communication requires relay satellites. The rocky terrain is rugged, dusty, and extremely cold at night. And any hardware must withstand extreme temperature swings and relentless radiation. But the scientific payoff is enormous. The far side of the moon may be the only place where the universe's earliest radio fingerprints can be observed cleanly and directly, without the noise of our own technological civilization drowning them out. In the end, the reason the far side of the moon matters is simple. If we want to hear the universe before the first stars existed, we have to go somewhere quieter than anywhere on Earth. And the moon's far side is the quietest place we know. How a 7,200 antenna array would operate. When scientists talk about studying the cosmic dark ages from the far side of the moon, they're not imagining a single giant telescope like the radio dishes we've built on Earth. Instead, the vision is far more futuristic, a sprawling network of thousands of small antennas spread across lunar soil, working together as one enormous unified instrument. This idea isn't theoretical hype. It's rooted in a proven technique called interferometry, the same method used by arrays like the Very Large Array in New Mexico or ALMA in Chile. But on the moon, the scale, the environment, and the scientific goal push the concept into a completely new category. A 7,200 antenna array on the lunar far side would be one of humanity's most ambitious scientific constructions, a structure designed not to look outward at galaxies, but backward in time, toward the first breaths of structure in the infant universe. The beauty of an array like this is that it doesn't need a single massive dish to gather faint radio waves. Instead, each antenna captures a tiny piece of the cosmic signal. By itself, that signal is too weak and too noisy to be useful. But when thousands of antennas work together, each sampling the sky at slightly different positions, their combined output can be processed into a coherent picture, a kind of cosmic jigsaw puzzle assembled through the mathematics of interferometry. Computers compare the timing, phase, and amplitude of incoming waves at each antenna, allowing the array to behave like one colossal telescope, whose effective diameter is as large as the entire network's footprint. That's why the number of antennas matters. The more antennas, the more baselines, the imaginary lines between each pair of antennas, whose distances determine the instrument's resolution and sensitivity. With 7,200 antennas, the number of pairings becomes enormous, meaning the array can probe the Dark Ages signal with extraordinary detail. The goal isn't merely to detect the hydrogen emission, but to map it across the sky, revealing how matter clumped, where it cooled, and how cosmic structure slowly began to form. These maps would finally fill in the blank space between the cosmic microwave background and the first galaxies, the missing chapter physicists have struggled to access for decades. But building such an array isn't something astronauts could realistically do by hand. The far side of the moon is remote, harsh, and difficult to access, especially with today's level of crude exploration. That's why nearly all proposed designs rely heavily on robotics. Swarms of robotic rovers, possibly autonomous, possibly remotely operated from a lunar relay station, would carry lightweight antenna units across the surface, placing them according to a pre-planned geometric pattern. Some concepts imagine antennas printed onto flexible, rollable sheets of material that a rover could unspool like carpet. Others envision spidery robots carrying small dipole antennas and anchoring them directly into the regolith. The deployment doesn't need perfect precision either. Tiny variations in positioning can be compensated for in the data processing stage, as long as the exact coordinates of each antenna are known. Laser mapping and onboard navigation systems would track each unit's location, building a real-time model of the array's structure. Once placed, the antennas require minimal maintenance. There are no moving parts, no complex mechanical systems, just simple receivers listening to long wavelength radio waves from billions of years ago. What happens next is where the magic of computation comes in. Each antenna collects raw radio data, essentially voltage fluctuations caused by incoming radio waves. These signals are fed into a central processing unit, either located on the Moon itself or transmitted through a relay satellite to a processing center in lunar orbit or on Earth. For a large array like this, local processing might be more efficient, because bandwidth limitations make sending all raw data back to Earth impractical. Instead, the lunar system could perform the initial correlation steps, combining signals pair by pair to extract meaningful patterns. Only the correlated compressed data, the scientifically useful part, would be sent home. This is the same principle used by Earth-based interferometers, but the scale and environment of the Moon introduce new challenges. The lunar day-night cycle spans 29.5 Earth days, meaning long periods of intense heat followed by deep cold. Antennas must withstand extreme temperatures, micrometeorite impacts, and ultraviolet radiation. Electronics need protection from cosmic rays and solar storms. Despite these difficulties, the simplicity of dipole antennas works in favor of mission designers. They can be rugged, power-efficient, and resilient. Powering a 7,200 antenna array is another engineering puzzle. Solar panels are the most practical solution, especially if placed on elevated ridges or nearby peaks that receive long periods of sunlight. Some proposals imagine small nuclear power units offering constant energy regardless of the lunar day. Either way, power distribution networks must connect the antennas or supply each one individually. Fortunately, the antennas themselves consume very little power. The computational systems require more, but even that is manageable with modern low-power processors. Once operational, the array would begin collecting the most pristine radio data ever recorded. Over weeks, months, and eventually years, the instrument would build an evolving three-dimensional map of the Dark Ages, tracing how hydrogen temperature and density changed across cosmic time. Because the hydrogen signal is redshifted, different frequencies correspond to different eras. Observing many frequencies at once allows scientists to construct a time cube of the early universe, almost like a CT scan of cosmic history. This is the ultimate prize, a view into the universe before light existed, captured from a silent world that never hears Earth's noise. A 7,200 antenna array on the Moon isn't just a telescope, it's a time machine. And if built, it would give humanity its first real look into the most hidden era of all. If futuristic observatories and ambitious space projects excite you, hit like and subscribe. Your support tells me to keep covering these long-term science bets, not just quick launch recaps. What we could learn. If we could finally detect and map the radio signals from the cosmic dark ages, the scientific payoff would be absolutely enormous. Easily one of the most transformative breakthroughs in modern cosmology. These signals come from neutral hydrogen atoms drifting through a universe that was still young, cold, and completely starless. And because this era sits far beyond the reach of our current telescopes, unlocking it would open a window into the most mysterious, untouched chapter of cosmic history. The moment we begin capturing these 21-centimeter hydrogen emissions, we're essentially taking the universe's first photograph, a snapshot of reality before the first stars ever flickered on. But the Dark Ages would show us the blueprint. How tiny density differences grew under gravity, forming clumps, filaments, and voids long before galaxies took shape. This is hugely important because those early patterns are governed mainly by dark matter. Regular matter was still cooling, floating, or falling in, but dark matter was already structuring the universe. So mapping this era would be like watching dark matter sculpt the first cosmic architecture in slow motion. This by itself would test our fundamental physics more powerfully than any collider or satellite today. If those early structures grow differently from what the standard model predicts, it could hint at new forms of dark matter, warm dark matter, self-interacting dark matter, or something even stranger. It might tell us whether gravity behaved differently at huge scales, or whether some unknown particle influenced structure formation. And because the universe was so simple back then, just hydrogen, gravity, and dark matter, any deviations from predictions would be incredibly clear. That clarity is something astronomers deeply crave. Today's universe is messy. Stars explode, galaxies collide, black holes distort space-time, and radiation heats and ionizes gas. But in the Dark Ages, none of that existed yet. It was the universe in its purest, cleanest form. We would also learn how rapidly the universe cooled after the Big Bang. Right now, our temperature curve for the early universe is mostly theoretical, guided by indirect observations. Dark Age radio signals would give us precise temperature readings across hundreds of millions of years. That means we could check whether the early universe cooled exactly as physics predicts, or whether some unknown energy injection happened somewhere along the way. These details help refine, or overturn, models of cosmic inflation and early universe physics. Another huge payoff would be understanding how the first stars eventually formed. Today, we know the first light era happened roughly 100 to 200 million years after the Big Bang, but the exact timing is still fuzzy. By examining how hydrogen gas gradually warmed, clumped, and collapsed, we could pinpoint the precise moment when the universe transitioned from darkness to illumination. That transition, called the Epoch of Rhionization, is one of the biggest mysteries in cosmology. The hydrogen signals from the Dark Ages gradually disappear as the first stars ionize them. By watching that disappearance happen spatially and over time, we'd finally understand which objects reionize the universe. Tiny newborn stars, giant early galaxies, early black holes, exotic dark matter interactions. This is a massive debate, and the moon-based array could settle it. Even more exciting, we could map how the cosmic web grew from simple hydrogen clouds into complex filaments stretching millions of light-years across. Today, we see the cosmic web fully developed, a vast structure shaped by gravity and dark matter. But with Dark Age data, we'd watch that web forming from almost nothing. Another treasure hidden in these signals is the ability to measure the universe's expansion at a time when it was still dominated by matter rather than dark energy. That gives cosmologists a powerful new data set to compare with today's expansion measurements, and may help resolve the controversial Hubble tension. If early universe expansion doesn't match predictions, it means our entire model of cosmic evolution needs updating. And then there's inflation, the rapid expansion right after the Big Bang. The fingerprints of inflation, tiny variations in density, would appear directly in these radio patterns. If we find exactly the distribution inflation models predict, it strengthens our current theories. But if we find something off, too smooth, too clumpy, or asymmetric, it could point toward new physics entirely. Challenges ahead. Building a massive 7,200 antenna radio array on the far side of the moon sounds thrilling on paper, but the challenges ahead are absolutely enormous. Some engineering, some financial, and some deeply practical in ways most people never think about. The moon is not just another place to build a telescope. It's an environment that actively tries to destroy anything humans put there. Temperatures swing from blistering heat to brutal cold by hundreds of degrees. There's no atmosphere to buffer electronics, no natural protection from radiation, and every component is battered constantly by micrometeoroids. Tiny, high-speed projectiles that hit the lunar surface all the time. Even dust becomes an enemy. Lunar dust is razor-sharp, electrically charged, and notoriously sticky. NASA astronauts during Apollo called it the #1 problem on the moon. Then comes the challenge of deploying it. No human team is going to manually place 7,200 antennas across kilometers of rugged terrain. That means robots. Lots of robots. Robots that can land, withstand radiation, travel across uneven ground, plant hardware with precision, connect power lines, calibrate equipment, and coordinate like a construction crew without human hands guiding them in real time. And since the moon's far side is permanently shielded from Earth, there's no direct communication link. Every command has to bounce through lunar orbiters, adding delays and complexity. This construction environment has no equivalent on Earth, and cost is the next mountain. Even conservative estimates put such a project in the tens of billions of dollars, potentially more once maintenance and replacement missions are factored in. Space budgets everywhere on Earth are already stretched thin by lunar landing programs, Mars ambitions, climate satellites, commercial launches, and defense priorities. A lunar radio array competes with all of that. And unlike rockets or GPS systems, this isn't a mission with immediate commercial return. But even if the array is built and powered, operating it introduces new difficulties. Thousands of antennas must stay precisely calibrated despite thermal expansion, radiation damage, dust accumulation, and mechanical drift. On Earth, technicians recalibrate radio telescopes regularly. On the Moon, no such easy maintenance exists. Autonomy becomes essential. The system must detect its own faults, isolate failures, and reroute data through working antennas to preserve image quality. Data transmission is also a huge obstacle. Mapping the Dark Ages means collecting staggering amounts of raw radio data, far more than current lunar communication systems can handle. The telescope will need on-site processing, compressing, filtering, and combining signals before sending them back to Earth. That requires powerful computers operating in low-gravity vacuum conditions with tight power constraints. Radiation shielding, cooling, and redundancy all become major engineering puzzles. And even after all those hurdles, there's the ultimate challenge: making sure the telescope actually works scientifically. No instrument like this has ever been built before, not even on Earth. Tuning a giant interferometric array to detect incredibly faint 21-centimeter hydrogen signals from over 13 billion years ago requires precision that pushes the limits of physics and engineering. Algorithms must remove instrument noise, solar interference, cosmic rays, and natural radio emissions from the galaxy. Errors that would be tiny in normal astronomy become enormous problems when signals are this faint. Entire new statistical techniques will be needed. Yet for all these challenges, and they are vast, the reward is equally vast. If scientists and engineers somehow overcome the environmental hazards, the cost, the robotics, the data issues, and the detection difficulties, the outcome could be one of the most powerful scientific tools humanity has ever created. This lunar array would let us look further back in time than any telescope in existence. We would be stepping beyond the limits of James Webb, beyond the reach of even the best ground-based observatories, into a time period that has remained completely dark to us. It would reveal a chapter of cosmic history that has only existed in equations and simulations. Until now. And the far side of the Moon is the only place in the inner solar system quiet enough to make this happen. So yes, the challenges are immense. But the prize, a direct window into the universe before the first stars, is profound enough that many scientists believe the effort is worth it. If humanity can pull it off, this array might stand as one of our greatest achievements. A scientific time machine built on another world, turning the Moon's silence into our loudest discovery ever. Humanity may be closer than ever to unlocking the universe's oldest secrets. The question is whether we'll dare to build the tools bold enough to reveal them. Do you think a lunar telescope like this will ever actually happen? And if we could see the cosmic dark ages, what mystery would you want answered first? If you enjoyed this deep space breakdown, make sure to like and subscribe for more mind-bending explorations.